up guys, our subject is ES6 Engineering Economics and this is Lecture 4. So we are still under Chapter 1, Introduction to Engineering Economics. Our lesson for today is Present Economic Studies. Present Economic Studies. When alternatives for accomplishing a specific task are being compared over 1 year or less, and the influence of time on money can be ignored, engineering economic analyses are referred to as present economy studies. Several situations involving present economy studies are illustrated in this section. The rules or criteria shown next will be used to select the preferred alternative when defect-free output is variable or constant among alternatives being considered. Rules in present economic studies. Rule 1. When revenues and other economic benefits are present and vary among alternatives, choose the alternative that maximizes overall profitability based on the number of defect-free units of a product or service produced. Rule 2. When revenues and other economic benefits are not present or are constant among all alternatives, consider only the cost and select the alternative that minimizes the cost per defect-free unit of production or service output. Total cost in material selection. In many cases, economic selection among materials cannot be based solely on the cost of materials. Frequently, a change in materials will affect the design and processing cost, and shipping cost may also be altered. Okay, we have example 2-8. Choosing the most economic material for a part. A good example of this situation is illustrated by a part of which annual demand is 100,000 units. The part is produced on a high-speed turret lathe using 1,112 screw machine steel consisting of 30 cents per pound. A study was conducted to determine whether it might be cheaper to use brass screw stock costing $1.40 per pound. Because the weight of steel required per piece was 0.0353 pounds and that of brass was 0.0384 pounds, the material cost per piece was $0.0106 for steel and $0.0538 for brass. However, when the manufacturing engineering department was consulted, it was found that although 57.1 defect-free parts per hour were being produced by using steel, the output would be 102.9 defect-free parts per hour if brass were used. Which material should be used for this part? Okay, so here is the solution. The machine attendant is paid $15 per hour and the variable overhead cost for the turret lathe are estimated to be $10 per hour. Thus, the total cost comparison for the two materials is as follows. Okay, so we have for material 0.0106 for steel, for brass 0.0538. For labor, we have 0.2627 for steel and for brass 0.1458. The variable overhead for steel 0.1751 and for brass 0.0972. So the total cost per piece for steel $0.4484. For brass $0.2968. Saving per piece by use of brass, so that is 0.4484 minus 0.2968 equal to $0.1516. Because 100,000 parts are made each year, revenues are constant across the alternatives. Rule 2 would select brass and its use will produce a savings of $151.60 per thousand. It is also clear that costs other than the cost of material were important in this study. Care should be taken in making economic selections between materials to ensure that any differences in shipping cost, yields, or resulting scrap are taken into account. Commonly, alternative materials do not come in the same stock sizes, such as sheet sizes and bar lengths. This may considerably affect the yield obtained from a given weight of material. Similarly, the resulting scrap may differ in various materials. In addition to deciding what material a product should be made of, there are often alternative methods or machines that can be used to produce the product, which in turn can impact the processing costs. Processing times may vary with the machine selected as may the product yield. As illustrated in example 2-9, these considerations can have important economic implications. Okay, so we have example 2-9. Choosing the most economical machine for production. Two currently owned machines are being considered for the production of a part. The capital investment associated with the machines is about the same and can be ignored for purposes of this example. The important differences between the machines are their production capacities and their reject rates. Consider the following table. So for production rate, we have machine A, 100 parts per hour. For machine B, 130 parts per hour. Hours available for production, machine A 7 hours per day, machine B 6 hours per day. Percent parts rejected, machine A 3%, machine B 10%. The material cost is $6 per part, and all defect-free parts produced can be sold for $12 each. For either machine, the operator cost is $15 per hour, and the variable overhead rate for the traceable cost is $5 per hour. Letter A. Assume that the daily demand for this part is large enough that all defect-free parts can be sold. Which machine should be selected? For letter B, what would be the percent of parts rejected have to be for machine B to be as profitable as machine A? Okay, so here is our solution. For letter A, Rule 1 applies in this situation because total daily revenues and total daily cost will vary depending on the machine chosen. Therefore, we should select the machine that will maximize the profit per day. So profit per day is equal to the revenue per day minus the cost per day. That is equal to production rate multiplied by production hours multiplied by the $12 per part, or the price that the part is being sold, multiplied by 1 minus the percent rejected over 100, minus the production rate multiplied by the production hours multiplied by $6 per part, minus the production hours multiplied by $15 per hour plus $5 per hour. For machine A, the profit per day is equal to $3,808 per day. For machine B, the profit per day is equal to $3,624 per day. Therefore, select machine A to maximize profit per day. For letter B, to find the break-even percent of parts rejected, X, for machine B, set the profit per day of machine A equal to the profit per day of machine B and solve for X. That is, the profit for machine A is equal to 3,808 per day equal to 130 parts per hour multiplied by 6 hours per day multiplied by $12 per part multiplied by 1 minus X minus 130 parts per hour times 6 hours per day times $6 per part minus 6 hours per day multiplied by $15 per hour plus $15 per hour. Making versus purchasing studies. In the short run, say 1 year or less, a company may consider producing an item in-house even though the item can be purchased from a supplier at a price lower than the company's standard production costs. This could occur if direct, indirect, and overhead costs are incurred regardless of whether the item is purchased from an outside supplier, and the incremental cost of producing an item in the short run is less than the supplier's price. Therefore, the relevant short-run cost of make versus purchase decisions are the incremental cost incurred and the opportunity cost of the resources involved. Opportunity costs may become significant when in-house manufacture of an item causes other production opportunities to be forgone. But in the long run, capital investments in additional manufacturing plant and capacity are often feasible alternatives to outsourcing. Because engineering economy often deals with changes to existing operations, standard cost may not be too useful in make versus purchase studies. In fact, if they are used, standard costs can lead to uneconomical decisions. Example 2-10 illustrates the correct procedure to follow in performing make versus purchase studies based on incremental costs. Okay, so we have example 2-10. To produce or not to produce? That is the question. A manufacturing plant consists of three departments, A, B, and C. Department A occupies 100 square meters in one corner of the plant. Production X is one of several products being produced in Department A. The daily production of product X is 576 pieces. The cost accounting records show the following average daily production cost for product X. So yung direct labor is equal to $120. For the direct material, the cost is $86.40 and the overhead cost is equal to 82. So the total cost per day is equal to $288.40. The department foreman has recently learned about an outside company that sells product X at 35 cents per piece. Accordingly, the foreman figured a cost per day of $201.60, resulting in a daily savings of $86.80. Therefore, a proposal was submitted to the plant manager for shutting down the production line of product X and buying it from an outside company. However, after examining each component separately, the plant manager decided not to accept the foreman's proposal based on the unit cost of product X. For direct labor, because the foreman was supervising the manufacture of other products in Department A in addition to product X, the only possible savings in labor would occur if the operator working 4 hours per day on product X were not reassigned after this line is shut down. That is, a maximum savings of $90 per day would result. For materials, the maximum savings on direct material will be $86.40. However, this figure could be lower if some of the material for product X is obtained from scrap of another product. For overhead cost, because other products are made in Department A, no reduction in total floor space requirements will probably occur. Therefore, no reduction in overhead cost will result from discontinuing product X. It has been estimated that there will be daily savings in the variable overhead cost traceable to product X of about $3 due to a reduction in power cost and in insurance premiums. Okay, so here is the solution. If the manufacture of product X is discontinued, the firm will save at most $90 in direct labor, $86.40 in direct materials, and $3 in variable overhead cost, which costs $179.40 per day. This estimate of actual cost savings per day is less than the potential savings indicated by the cost accounting records, that is $288.40 per day, and would not exceed the $201.60 to be paid to the outside company if the product X is purchased. For this reason, the plant manager used Rule 2 and reject the proposal of the foreman and continue the manufacture of product X. In conclusion, example 2-10 shows how an erroneous decision might be made by using the unit cost of product X from the cost accounting records without detailed analysis. The fixed cost portion of product X unit cost, which is present even if the manufacture of product X is discontinued, was not properly accounted for in the original analysis by the foreman. Trade-offs in energy efficiency studies. Energy efficiency affects the annual expense of operating an electrical device such as a pump or motor. Typically, a more energy efficient device requires a higher capital investment than does a less energy efficient device, but the extra capital investment usually produces annual savings in electrical power expenses relative to a second pump or motor that is less energy efficient. Hence, the purpose of this is to explain how the annual expense of operating an electrical device is calculated and traded off against capital investment cost. If an electric pump, for example, can deliver a given horsepower or kilowatt rating to an industrial application, the input energy requirement is determined by dividing the given output by the energy efficiency. If an electric pump, for example, can deliver a given horsepower or kilowatt rating to an industrial application, the input energy requirement is determined by dividing the given output by the energy efficiency of the device. The input requirement in HP or kilowatt is then multiplied by the annual hours that the device operates and the unit cost of electric power. You can see that the higher the efficiency of the pump, the lower the annual cost of operating the device is relative to another less efficient pump. Okay, so we have example 2-11, investing in electrical efficiency. Two pumps capable of delivering 100 HP to an agricultural application are being evaluated in a present economy study. The selected pump will only be utilized for 1 year and it will have no market value at the end of the year. Pertinent data are summarized as follows. For ABC pump, the purchase price is 2,900, maintenance cost 170, and efficiency 80%. For XYZ pump, the purchase price is 6,200, maintenance cost 510, and efficiency 90%. If electric power costs 10 cents per kilowatt and the pump will be operated 4,000 hours per year, which pump should be chosen? Recall that 1 HP is equal to 0.746 kilowatts. Okay, so here is the solution. The expense of electric power for the ABC pump is $37,300. For the XYZ pump, the expense of electric power is $33,156. Thus, the total cost of owning and operating the ABC pump is $40,370. while the total cost of owning and operating the XYZ pump for 1 year is $39,866. Consequently, the more energy efficient XYZ pump should be selected to minimize total cost. Notice the difference in energy expenses, that is 4,144, that results from a 90% efficient pump relative to an 80% efficient pump. This cost reduction more than balances the extra $3,300 in capital investment and $340 in maintenance required for the XYZ pump. So that ends our lecture 4. See you next lecture.
Magbabaksakan dito in 5, 4, 3, 2.
1, 2, 3, 4.
DJ Joanna sa